You've been reading about how the shape of an orbit is an ellipse. So today I want to take a look at what the difference is between an ellipse and a circle. If we wanted to draw a circle, we would have the center of the circle, and every point on that circle is the same distance from the center. So you have a constant radius. So we can do that by taking a little push pin and a loop of string. And if I put my pen here, I can make a circle having all of those points the same distance from the center of that circle. So from here to any point on the circle is going to be the same distance, which is the length of the loop completely stretched out. Now it is a little bit off here just because the string's a little bit stretchy. But that's a circle. An ellipse, instead of having one center, kind of has two. And it's not the distance from the center to the ellipse, that's the same. It's, if I take this and draw this, it is the sum of the distance from one focus to the ellipse plus the distance from the other focus to the ellipse. So if I add this plus this, it's always equal. So the two push pins, those two kind of centers, are called the foci, which is the plural of focus. For an orbit, or for a planet's orbit, one of those foci is the sun. The other is nothing. There's nothing actually there. It's just mathematically, there's this other point that when I add the distance from the sun to the earth plus this other thing, other point to the earth, that sum is always the same. But there's no actual object here. And one of the reasons we know that is the focus is different for every single planet. So for every planet's orbit, one focus is the sun and the other focus is somewhere else. The farther apart the other focus is from the sun, so how far apart those two foci are, the more squished that circle becomes. So we're looking at, this is a perfect circle where kind of both of the foci are on the same point. As I move farther away, it squishes it a little bit. Farther away, it squishes it even more. So this isn't just any oval, it is really a specific type of oval that has a specific mathematical relationship to it. But what you need to know is the sun is one focus for every planet's orbit. For the moon's orbit around the Earth is one of the foci. So one focus is the thing that it's orbiting around. The other focus is just some other point in space. Now, if we wanted to calculate the eccentricity is a measure of how squished that circle is. So we're going to put in our two foci and draw the ellipse. In order to measure to calculate the eccentricity of the ellipse, what I need to know is the distance between my two foci. So we'd take a ruler and we would measure that distance. And then we would divide that by what's called the length of the major axis. The major axis is if you take the line that goes through the foci and extend it to the ellipse itself. So that major axis is kind of like the big diameter of the ellipse. So you would take this distance, and let's say this is 2 centimeters. So we'd take the distance between the foci and divide it by the length of the major axis, which let's say that's 7 centimeters. I don't have a ruler here right now. And we would get our eccentricity. So 2 divided by 7, which would be about 0.3. Notice I have units of centimeters on the top and on the bottom. Those units will cancel each other out, so it doesn't matter what unit you're measuring your foci and your major axis in. There will be no unit to this. The eccentricity is just a number. That number can be anywhere from 0 to 1. If my 2 foci are on top of each other, meaning I have a circle, the distance between my foci would be 0. 0 divided by anything is 0. So an eccentricity of 0 is a perfect circle. If I have those foci spread so far out that they're actually along that major axis, so kind of like this, when I go to draw my ellipse, it's essentially just a straight line, and this one didn't draw too well because it's so stretched out. But an eccentricity of 1 would actually be a straight line. So the distance between the foci is equal to the length of the major axis, and there would be no up and down portion to that. So your eccentricity is going to be somewhere between 0 and 1. The closer to 1 it is, the more squished your circle is going to be. The closer it is to 0, the closer it is to a perfect circle. Now, one other thing that we talked about is the fact that because we have an ellipse for the shape of our orbit, the planet is not always the same distance to the sun. Sometimes it's closer to the sun, and sometimes it's farther from the sun. So let me draw another ellipse. All right, so the yellow one here is going to represent the sun. The red one's just that other point that gets me to the ellipse. So there are times where the planet is closer to the sun, and there are times when the planet is farther away from the sun. Now, this is not what causes seasons. If you look at the eccentricity of our orbit, it's not all that squished of a circle. So the distance from the sun is actually not going to affect the seasons. It's not going to determine whether we're warmer or colder. It actually happens that we're closest to the sun in about January and farthest from the sun in July. We'll talk later about what causes those seasons. But the Earth is going to move at different speeds in its orbit at different times, or because of the different distances to the sun. So you read about Kepler's law, and what Kepler's law says is that it travels faster when it's close to the sun and slower when it's farther away. So if we're going to look at the amount of distance that the Earth travels in its orbit, when we're close to the sun, we maybe travel this far during the month of January when we're close to the sun, and only that far in July when we're farther from the sun. So we travel a greater distance in that same amount of time when we're closer to the sun than we do when we're farther from the sun. Again, this is not what causes the seasons. We'll talk about that later. But we are moving at different speeds in the orbit. The time it takes for any object or for any planet to move around the sun, the time for its revolution is 1 year. So Earth's year happens to be 365 days, so it takes us 365 days to complete one complete revolution around the sun. Other planets have years that are different amounts of time, and ones that are closer to the sun are going to have shorter years, meaning it takes them less time to revolve around the sun. Ones that are farther away have longer years. Their revolution is longer. So an ellipse has two foci that kind of squish the circle. The eccentricity is the distance between the foci divided by the length of the big diameter, which is called the major axis. A smaller eccentricity is closer to a circle. If it's closer to 1, that squishes it more and more and more. The closer an object is to that sun, the object it's revolving around, the faster it's moving. The farther away, the slower it's moving. So when any planet is closest to the sun, it moves faster. When it's farther away, it moves a little bit slower.